All right, students, let's go to a new topic within this chapter 10. Okay, so the name of chapter is second moment of area and moment of inertia. Okay, so again, the moment of inertia is a terminology where basically is very frequently used in comparison to second moment of area. We call it moment of inertia, but the second moment of area and moment of inertia are totally different things. Movement of even though their symbols are quite similar, like I second symbol is ix and iy, moment of inertia symbol is im, but they are basically conceptually very different quantities. Second moment of area is used in structure designs, in mechanical components. When we civilian structures design, we use it a lot. In column design, we use it. But moment of inertia is basically a dynamic quantity. Okay, so it is basically used in basically rotational dynamics. It is used a lot in basically mechanical structures components, and it is also used in vibration. A lot rotational dynamics. Okay, when we are designing mechanical uh, machine design components, we use the moment of inertia as a lot. Okay, so you must remember that it how you define the how you define second moment of area. It is simply defined as the resistance to bending. Second moment of area is defined as the resistance to bending. How would you define moment of inertia? It is the ability, if you look at it, if you look at just wait, it is the ability of a body to resist angular acceleration and deceleration when the body is in rotational motion about an axis. Okay, so when the body is in rotational motion about a specific unique axis. Okay, and it could be under basically acceleration or deceleration. Over there we will use the moment of inertia. It is a function of the mass distribution of the body and also its geometry. Okay, so how the mass is distributed and what type of a geometrical cross section is engaged. Okay, it depends upon them. Okay, it is most often used, again as I've told you. This quantity is basically im is given as equals to, again very similar to second moment of area if you look at it, but you can see the difference. It is called moment of inertia. Im is equals to integral of r square dm, integral of r square dm. Okay, and basically what density is equals to mass per unit volume. So what is mass going to be equals to? Mass is nothing but it's a product of density into volume. So we can replace integral of r square dm with integral of r square times rho times dv. Okay, so we can do that. So im again is the moment of inertia of the body. Okay, and r is, what is this r? This r over here which is there, it is the perpendicular distance of the mass from the axis of rotation. So this is very important to understand that the formula is r square dm. Okay, you must be able to, if you look at it here, uh, if I go to the next slide, this is again, if this is the body, this is our unique axis, and this is the mass m, and this is the perpendicular distance from this axis is r. So r square times of multiplied with the mass will give me the second so the moment of inertia of that body about this specific z axis. Okay, so its value will be different about different axes of rotation. What does that mean? It means if it is about z, it will be different. If we about y, it will be different. If it will be about x, it will be different. So it's depending upon the axis. Okay, so what is trying to tell you over here? Formulas are also available again for simple shaped bodies. They have got different formulas. Like for thin rods, circular disc, and plates, you have got specific formulas for it. Okay. Also, for composite bodies, integration can be converted to summation signs. So you already know, like if you have got composite bodies over there, you can basically instead of integral sign, you can use a summation sign. So this is very simple. And if the body is not composite, it is any shape or specific type of over there. Uh, it is given, so we can use an integral sign for that and perform the integration with respect to specific limits as defined along x and y axis. Okay, just brief how to about the application. It's used in car flywheel. If you look at it, uh, whenever you change basically your uh, your clutch system of a car, you have a flywheel, okay, which provides the initial inertia, and because of which the engine starts to rotate. It basically stores the energy, okay. So flywheel, due to their higher moment of inertia, are used in power generating machines. That your engine is a power generating machine to keep the output power uniform. Okay, hollow shafts. It's used in hollow shafts to transmit more power, more torque to solid shafts compared to solid shafts due to the higher moment of inertia. Okay, shifts moment of inertia are also made higher. About the, again, these hollow shafts can be used in as a as propellers in ships. Okay, if you go and see a ship from the in submarines, we use it. So because why, it has a higher moment of inertia. Okay, so ship's moment of inertia is made higher about the pitching axis. Again, this is the pitching axis. Its moment of inertia is being made more higher. Moment of inertia is being more made higher. Okay, so that stability of the ship is being increased. If basically for about the pitching axis. Okay, so higher moment of inertia is required to make mechanical structures. Again, in order to make mechanical structures more robust against vibration, okay, you need to have a higher moment of inertia. Okay, so again, if you look at it, these modern cars which are common, if you see, you have very little vibrations because their engines are very much accurately designed. Their moment of inertia is ideally designed so that very minimum vibration is transmitted in like in Civic and Corollas to the occupants who are sitting in the car. So you must remember as an extra knowledgeable point from moment of inertia's importance. Okay, and again, in final year you will study this subject which is called as the mechanical vibration. It's a very challenging subject, so you will be using this moment of inertia a lot. Okay, another just a brief reminder that over there you have just studied in second moment of area parallel axis theorem. Okay, since I told you they are very similar, you also have a parallel axis theorem in moment of inertia. Okay, so like over here, the moment of inertia about about any axis. Okay, if you have calculated the moment of inertia, okay, so parallel axis theorem is basically similar to that. So I is equals to ig plus md square, where ig is the moment of inertia of the body about the axis. Okay, it is basically about the center of mass of the body. It is the axis about the center of mass. Okay, m is the mass of the body, and d is the perpendicular distance between the axis. Okay, so then again, if we have this body which is basically r times m, okay, r square times the integral of dm, we already know this body's angular velocity will be given as omega, and this body's tangential velocity will be given as v equals to r omega. So the linear kinetic energy of this particle m will be half mv square, but the rotational kinetic energy of this body is given as half, again, m times what is v. V is basically the, since it's rotational, we'll be dealing with tangential velocity v equals to r omega, so it becomes half m basically, and for v basically v square we place r square omega square. Okay, now this terminology mr square actually is basically being termed as uh, the moment of inertia of the body. Okay, and if you look at it, is you compare these equations for linear kinetic energy, this is m, but when we take the rotational kinetic energy, it is replaced, this m is being replaced by mr square. And what is mr square? Actually, if you look at it, it is nothing but it is the uh, analog of inertia. It is basically the uh, uh, basically the moment of inertia of the body. Okay, so the term mr square appears too frequently in rotation dynamics, is symbolized as im, and sometimes it's also being symbolized as J, okay, as the moment of inertia. Okay, it should be noted that this Im is also equals to r square integral dm. If you integrate it, you call it r square m, is only valid for a single particle. Okay, so one single, but for majority of the particles, or if you have a for whole body, you can apply the concept of integration. Okay, uh, so for infinite number of such particles, we can apply the concept of integration. Okay, at different points, therefore the rigid bodies, we use the concept of integration. So here we write it as Im is equals to integral of r square dm. This is uh, the moment of inertia of the body, uh, whose basically r. So if we integrate it with respect to this integration, it becomes Im is equals to mr square. Okay, so this is all about the moment of inertia of the body, and now we start with the numericals of how to calculate the second moment of area, how to calculate the moment of inertia of the body, to understand our concepts better. So always remember this formula is very important, and because here the concept of mass is being applied, and when we apply the moment of inertia of the body, we can also apply the parallaxis theorem on it, where I equals to Ig plus md square. This Ig is basically the moment of inertia of the body about the axis which is passing through the center of mass of the body. M is the mass of the body, and d is the perpendicular distance between the axes. So you must remember these type of things, and very important that the applications of the moment of inertia is also very important. So with these concepts understand theoretical, now we can easily shift over to the numericals. So I thank you very much, students. Jazakallah. Allah Hafiz. Thanks.